Okay, welcome to part three of our devices discussion. Last time we discussed the device state engine. So what actually runs our state machine logic and transitions, step numbers, gives us some useful diagnostics like bitwise state status, along with some other features that are just nice to have. So today our discussion is going to basically be a demonstration of how we add a new device into our system. And we are going to perform this with our washer device. So currently I already have a washer device in the system, but I'll just kind of walk you through where that washer device lives, and then we will work on converting the washer device logic from its current logic to a device state machine. So buckle up, should be a good one. So I've got Codesys open here, and I'm going to go ahead and save this project. Let's do a duplication just in case something weird goes on today, but go ahead and update that. All right, so again, the idea with our device is that it's a collection of inputs and outputs, motors, actuators, and we want to be able to kind of control that individual device from another device, from a parent device. So in our scheme, you remember we had, I'll go to our device hierarchy. So if you look, nested with inside conductor and inside robot, we have this washer device. So ultimately the washer device will belong to the robot. So we'll want to make sure we structure our device and put our device function block in the correct place. So basically, the parent device to the robot is a conductor, and the child device to the robot would be the wash. So the washer's parent device is the robot. So let's go ahead and look and see how we start off with adding a new device to our system. So um, kind of the first step that we typically do is we would want to just add or declare the device kind of globally. So we do that in a couple different manners. So we come first to our believe it's in our source code. Um, let's see, system device IDs. There we go. So we were adding the washer for the first time. Basically, this wouldn't exist here, and we would kind of just add this to the end. So we want to give it a mnemonic or a shorthand name. Um, so in this case, I chose wash, and then you want to just sequentially add that wash station in here. And you give it a 17. If I didn't have anything, in that placeholder right there, I would add the wash in there like that, and then everything would be happy. We want to try to keep this enum in order from 0 through the last number, and we want to keep everything populated. So if you end up deleting a device out of the system, let's say we deleted washer, and we didn't let's say we deleted a device and we didn't have a replacement, you'd want to basically um, I guess you'd want to leave it as is, but it's just not good practice, I guess, to leave an empty space. But um, right now our user interface is looking at this enumeration, and so some of this Some of these device IDs, I guess you don't want to change, but I would say best practice would be, if you're adding a second, let's say we're adding a second washer, wash two, and just keep revving up. And let's say this washer no longer existed. You just do something like that. No harm, no foul. But I don't think you want to go around. You definitely want to avoid changing the device ID once you've already created it, particularly when it comes to the user interface, and how we define some of the tags in the user interface. So for now, for this demonstration, let's just pretend like we added it here. So wash 7. So that's the first place we want to add it. The next place we need to add it is in our main. So in our main program, when we declare variables, main is a way for us to declare kind of global scope variables. In Allen Bradley world, these variables that I have in main would be kind of considered global variables. In Allen Bradley, you kind of have program-specific variables, and in our case, we have function block-specific variables. But the global variable, there's a couple ways to define them. You can actually create a global variable here, but more often than not, you're going to want to add it likely into main. So specifically with devices, we definitely want to add it into main. And so you see in main, I kind of have these data variable chunks split up. If you come down through here, you'll see a couple different areas where I'm instantiating some variables. So in our case, this wash device variable was in here. So let's pretend like it wasn't there. So we'd want to create a new variable name. So we want to call it wash. We want to call it the same thing that we defined it as in our device ID, just for good practice. And then reference to device. Basically what we're doing with this statement is I actually have an array of devices that I list up here. And that array is basically the length of this device count, which is 17. So we want to update this value if we're adding a device into our system. But basically, we're going to use this devices array in our fault monitoring function block rather than these individual device variables. But the convenience of defining an array, we'll kind of see that come to play, but it's also convenient to break it out into its own individual. And so the way that we do that without, I guess, having to copy variable data between the device array and the individual device is we use references. So a reference is really kind of it's a pointer to an address. It's a little bit more than that, actually. It's a pointer that also builds, it appropriately gathers the data and builds it into a data chunk that you can use. So reference, you can kind of look up that documentation in Codesys and see how the differences between references and pointers. But references just allow us to basically create an alias to an existing data tag. So in this case, we are aliasing our wash tag to a data type of type device. So we're using this device data structure, and we need to tell it here, the assignment, we need to tell it which specific element in that devices array that we want to use. And so an easy way to do this, again, is to reference that enum. And so that's why I want to make sure we're keeping that enum kind of sequential, because it is ultimately corresponding to this device array. So once we instantiate that wash device here, the next thing we want to do is go modify this global constant device count. So if we were adding a new device, we would change that to 18, but since we didn't really add a new device, we're going to keep it as 17. But a good check that you can perform here is basically starting at 0, count your devices up. So basically just add 1 to whatever 16 is, and that's how many devices you have, or add 1 to whatever the last value is here. So 17 devices in total. So once we've updated our device count in this global constant, and we've added the device, added the device into the main program. Now this device can be accessed globally, and we'll see how we do that. So let me just verify we don't need to do anything else here. If the wash, yeah, so there may be some new data that you'll add in here. If the wash has a handshake data type, you would add it in here. Typically it would look something like this: wash, and it would be of type wash handshakes. Should be yelling at me right now. Yeah, so wash handshakes isn't a real thing. But yeah, if we created a custom handshake for wash, we would add it there. But since we don't have one, I'll just comment it out. And then same with wash data. Sometimes if you have device-specific data, you put it in here, and then you add it in here. And we'd first have to create this variable type wash data. So typically, what I'm doing when I'm adding a new device is, we'll come down into the source folder and we'll add a new folder for your new device. And then inside of new device, we'll add another subfolder. We'll call it data types. And then within data types, you can create and add a new object, and you could call that new dev data. And typically that's going to be a structured data type. And then here you can add some data structure, some data values that you want for your new dev. So on and so forth. So just kind of add that in there. So for the wash station, we already had this wash data type here, and so basically the only status or information that's used globally is this dryer blowers are on. So that's kind of the only thing that we're exchanging with the outside world. So I think that the naming convention oftentimes is pretty self-explanatory, and I try to write it like that so I don't have to do a bunch of work commenting. Well, not only that, but I think if you write variables that are well named, and people can read what's going on in the variable type, then they can take a guess at what this actually means. It's like, okay, dryer blowers are on, like the outputs for the dryer are on. That's what that means. Sometimes I like to define if it's true, what the outputs are on, if it's true, or something to that nature. So anyways, added wash data there. we instantiate that wash data variable in main. So here in main, you would add it right there. So, kind of just add it along with the other device specific data types. Um, so, let's see. Outputs. So inputs and outputs. We generally will define device level inputs and outputs here, and then I'll show you how we add that to our global variable inputs and outputs that we use for mapping. So for our washer, we don't have any inputs, but for outputs, we just come in here, we add an object. Let's say, for example, we did have some inputs. So wash inputs. Again, it's going to be a structure, and you can look at how the other devices do it, and see. You can monkey see, monkey do, see the pattern. What's the robot outputs look like? Well, it's a bunch of booleans. So, yeah, for inputs, we could add, if there was like a pressure switch for perhaps or maybe there's like a water level switch. I can actually see us implementing that. So, you'll notice my naming convention for inputs and outputs kind of has this underscore, and then I have this all caps. And that generally, what I'm doing there is I'm defining, okay, when this value is true, what is it actually telling you? So in this case, if true, the water level is good, is normal, is acceptable. If the water level was too low, that switch and the switch would not be on, then that would be a bad thing. You may have a case where maybe the switch is normally on, and then when it's not good, it's off. Or sorry, when it's not good, it's on. And so in that case, I might say something like normally closed or whatever. But in this case, the way that I'm naming these inputs, I know it looks different than how I name all the other variables, and that is design intent from my standpoint. I want it to look different, and I want you to be able to read the state here. So when true, what is the status? So water level switch underscore, okay. So generally I put the sensor, the sensor name here, switch okay. So we'll go ahead and just leave that in here for now. You may end up using it in the future, so I think you should. So wash inputs. Okay, so once we define those data types, wash inputs, then we want to add those to our inputs global variable. And this is, again, the inputs global variable here is something that we are updating in our IO map in our system level function block. And I'll show you where we do that at. So here, I have basically defined, again, this substructure. I named it after the mnemonic of the device. So in our case, if we had wash, I would add wash inputs. Okay, and so once we go there, and I'll just show you for completeness how we do it for the outputs. Ha, surprise, same. Do it the same way. Cool. All right, so when we add those in, we'll eventually need to map them to some Ethernet IP device, right? And so the idea is that for sensors and outputs, we want to do that kind of in one convenient location. And I house that in the system level stuff in the IO map. And so the IO map, this whole structured text, again, is just broken up by the physical I/O device that's collecting or setting the outputs, collecting the inputs, setting the outputs. So we got the pills controller, SMC valve bank, FANUC controller. So in our case, it's possible that we would add it, and let's say we would likely add it to this slot 2 in the digital input. So I'll just write inputs.wash.water level switch OK equal to, so there's this other variable, it's a global variable, SMC. This SMC input. So if you look where we ended up and where I've been housing these Ethernet IP device data types is up in this packages folder. So within packages, Ethernet IP devices, I created a data structure for the inputs. So in this case, I have a byte for digital input 1 and for digital input. So this is like specifically like an input module. So it only has 8 points. 8 points of digital input. It's possible when you add, originally we were supposed to have 16 point inputs. So if you ever replace the physical digital input module, which is 8 points, with 16 points, with a 16-point module, you would want to change this data type from a byte to something like an int, because an int has 16 bits. Our byte only has 8. But maybe we'll just kind of show you, I'll just kind of carry this example through and show you how we're kind of mapping this variable type to the physical device. So DI1, DI2, all right. So for the output module, I have this DO3, DO4. That's again an output module. And I used a sequentially increasing number for the slot number, so it's number 3, slot 3. That's probably a better way to write that. Slot 4, valve. Let me do the same thing here. Let's see. Module in slot. Okay. Good to go. All right, so coming back to here, so let's say this is SMC Ethernet IP dot input dot DI2.4. Okay, so that .4 is basically corresponds to the input 4 on the digital input module number 2. So digital input module number 2. So it'd be input 4. So input 0, 1, 2, 3, 4. So if you wanted to land a sensor for that water level switch, this is where you could do it, right here. And there's really no harm in leaving this logic in here for right now, even though it doesn't necessarily mean anything. Might be a good place for it to do. But you guys will realize it's not working, or if you plug it in, it doesn't work. You'll eventually get to this function block. So let's see. I want to carry this example through to the actual device. We'll go to the SMC. I just want to kind of show you again, like another example of Ethernet IP mapping, like how we're mapping these modules. So if we look in the SMC Ethernet IP, and we come down to the assemblies section. So assemblies section, I kind of try to name it the same way as that data type that I'm going to map it to. But you can see my digital inputs. Actually, this isn't named correctly. Target to output, so that's an input. So we might want to just go ahead and correct that. And I don't know which one's correct or not, but I'm just going to assimilate them. So when I change that, it doesn't really do anything other than just changes what is written here. But aside from that, the mapping stays the same. So you can see right here in DI1, this is the actual global variable, right? So that global variable that I was using here, SMC Ethernet IP, that's what is inserted here. And so I'm just mapping these data chunks to the corresponding global variable data structure. So if you end up changing the digital input, for example, to something that's 16 point, you would have to come into these assemblies and you would have to change this data chunk to, to be an integer. And then you'd have to make sure your connection size matched that as well. You want to increase this input target to object as an input. You want to increase that from 3 to 5 because you'd be effectively adding two new bytes. But since we're not doing that, I'll revert that back. So I can name this anything. I can name it whatever, blah, 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 blah. And if we go into the Ethernet IP mapping, you can just see it took it right here, but it didn't change anything about how I'm actually mapping to this SMC Ethernet IP global variable. So you may be asking yourself, why did you go through the step of, it seems like I'm double mapping, right? I'm mapping to a global variable, this SMC Ethernet IP global variable, and then I'm mapping that in the input output to a device variable, right? So why could I not just do this, do this here in the SMC? And the short answer is I could absolutely do that, but I believe for simplicity's sake, DI1, DI2, it has no specifics at this point. So if I wanted to copy the this SMC module, right, and paste it into a new project or something like that, and I want keep all this mapping, the only thing I would have to do is just add back in the this packages folder. I just add that into my project, and then boom, like it's all mapped. And then on that project, maybe DI1, input 2, maybe it's actually different. Maybe it's completely different. Well, I don't have to really take care of that here. I can just take care of that in one single place, which is in my IO map. So here it's much easier for me to kind of, correlate the Ethernet device variable to the actual sensor variable. So this basically, this list here should just look like your IO map, your Excel spreadsheet IO map. And so it's very easy to create this. Hell, you could probably automate it from the an Excel macro. But I prefer to do this sort of double mapping. I don't know if that's the correct term, but I prefer to do it like that because I felt like it was easier to kind of trace things through and modify things and move things around. Um, you can feel free to agree or disagree with me, but you know, I just recommend, spending some time and working with some of the Codesys style of creating Ethernet IP devices. Look at the challenges behind, you know, adding in, um, adding in individual bits here versus a whole data chunk. There's definitely some trade-offs. It's much easier to just write, a whole bytes worth of data here and break it out elsewhere. But it's kind of player's choice. But effectively, that's what I'm doing for the SMC, and do a similar thing for the pills, Ethernet IP. So if we happen to have some I/O cards on our PLC inside of our electrical enclosure, I would still do it like this. I would still absolutely do it like this. So this would just say, PLC Ethernet IP dot I dot, digital input 1, digital input 2, so on and so forth. All right. So, I know we kind of spun off into a discussion about I/O mapping, but I think that probably helped see, a good example of how we would add in an input. So again, we saw that, added it in. So now when I go to use this input, this global variable, um, I can conveniently start to write inputs dot wash dot, and then boom, I've got a list of all my wash level sensors. Or maybe if I'm in the robot, then it's like, oh, I got a collection of all my robot sensors. So it's definitely some nice features to doing it like this and taking the time to structure it like this. So inside of our um, actual wash device, we'll actually map an internal variable called I. We'll map it to this inputs.wash, and we'll just do a reference to this inputs.wash. And then so inside of our device function block, we can just write I dot, and then it'll show like water level. So it helps kind of reduce the overall length of the variable when we go to add it into the logic, which is kind of nice to do. All right, so on our kind of checklist here of adding in a new device, we instantiated it in the main program. We created our new variable data type, wash data. If we had a handshake, we could add it into here. Maybe I'll just go ahead and do it. So if I wanted to create a wash handshakes data, where should I put that? Well, let's put it in our wash component, our wash device component folder, and add it to data type. So we'll add this object DUT, which basically is a UDT in Allen Bradley. So I like to do, for whatever reason, I'm doing the mnemonic and then data handshake. Actually, this one's handshakes. So it's another structure. So add structure in here, and let's say we had something like run dryers request. So somebody's wanting to run our dryers. The washer, when I originally concepted the wash mechanism, it was going to be kind of a combination of a dunk tank. So you would have like a 2-position cylinder that would dunk the parts rather than having the robot do it, and then bring it back up. And then, while it's ascending, I would also turn on the dryer. So I may have added, run, dunk parts request, or whatever. Now, sometimes it's kind of nice to treat these devices like microwaves. So if you just, use the generic start command that comes already embedded, if there's not really, it's not really high complexity device, that's the simplest form. But, just to carry this example out, let's say the wash mechanism was more complicated and we had to choose times when we told it to dunk the parts versus running the dryer, and we would do it here. And then we want to make sure we add in um, our done bit. And I believe, just want to make sure I'm getting this dn, so I actually use dn, not done, in a shorter notation. But basically, this is the incoming command, and this is basically the acknowledge. It's actually not acknowledge is typically like, hey, I acknowledged you gave me the command. This is more like, I'm finished with doing what you told me to do. Command is done. Okay, so I'm either going to give you this bit or I'm going to fault out. So if you give me a run dryers request, I'm going to do what you told me to do, and you're going to wait and sit there, and you're going to hold that request, and you're going to wait until you see the run dryers done bit, and then you're going to drop your request, or you're going to see me fault out, trigger an error, and then you're going to react yourself in your logic. Only two outcomes possible. So let's go ahead and leave that in here. It's really no harm. Wash handshakes. So you'll see back to main. So inside my main, in my variable declaration, added this wash handshakes. And the reason why I'm defining it as a global variable is because that way, typically it's only your parent that's going to have access to the handshake, but at least this would enable everyone to have the ability to handshake with me if that was desired. So this is just good practice where I'm putting it here. Just keep it consistent. Define this wash handshake here. Okay. Can I move these variables? Just doing a little reorganization. So got all the devices. Device data and handshakes, device list. So we've got all the overhead as far as like declaring the device globally. So we did our homework there. So the next thing that we would need to do is create a new device function block from our package template. So device, I have this device function block template. We would just copy this code, and my intention is to put this inside of the this. I'm actually going to rename this. So a nice thing about this refactoring is wherever I have that wash instantiated, it's going to rename it for me. So go ahead and hit OK. So when I go to add my copy of device template function block, I'm going to rename this to wash function block. Then there's no confusion. So I added in my wash function block. Let's open it up. Okay, there's, again, just cut, copy, paste. So before we get too crazy, I'm actually going to jump in and I'm going to go to the place that we want to instantiate that function block, which is going to be inside of our robot. Again, I decided in my device hierarchy to have the wash be a child of the robot. And originally, when I first defined the hierarchy, wash was at the top with, CNC robot rack wash. But once I started to think about it, at least how we were using the wash, once Martin came on board and we decided to wash the parts with the robot, to me, it was similar to the deburr. It's like, well, the deburr mechanism, the deburr device doesn't work without the robot, and it's the same with the wash. So that's why I decided to lump it into the robot. Um, and really, the only person who's requesting to use it is going to be the robot. I think had we stuck with the dunk mechanism concept, I would have kept wash in outside of the robot and in, as a child of conductor, and then the robot can load it, and then the conductor would basically tell the dunk mechanism to start to, run the dunk and dry process. But that's not how we're doing this. So if you end up going to a system like that where you load it into a wash mechanism, then you know my recommendation would be to move it out of robot and put it into a global task, and then, sorry, a conductor child uh, device, and then you would have to create a new task in the conductor task planner to call the to call that program. I let's see, hold on just a second.